Hello, my name is Thomas, and this is my final project for Computer Science E-95 compiler design and implementation. In this project, I built a compiler for a subset of the C programming language. The implementation language is also C, and the compiler generates code for the MIPS CPU architecture. There are two programs I'd like to try the compiler on. The first computes the greatest common divisor of two integers using two different algorithms and compares the results. If they're the same, it'll print to the screen. So to build our compiler, we type make. To compile a program, we use the compiler executable followed by the source file. And this generates MIPS code, which we can take a look at the first 20 lines of the MIPS code. See the assembly instructions there. And then we can execute the MIPS code in the SPIM emulator. And for our GCD algorithm, we can enter two numbers, do 45 and 30. The largest number that fits evenly into both of those, divides evenly, is 15. The second program I'm going to show generates Sierpinski triangles. So this one asks for a power of 2 and then prints a Sierpinski triangle. Try that again with a bigger number. There you go. I will demonstrate different stages of the compiler on this simple.c program. To run a particular stage, we pass in the -s flag. We can pass in -s scanner to get the tokens. And you can see that we store the line number here, so we can display error messages later. The next stage will be the parser, which takes the program and turns it into an abstract syntax tree, and then takes that abstract syntax tree and outputs a pretty print of the program. So we could go ahead and mess up the formatting of this program and run it through the parser stage again, and we'll get the same pretty print. We can even run the pretty printer through the pretty printer itself, and we should get the same output. I like to use the tool Clang Auto Format, so when I saved my code, the code auto formats, it was interesting to see how such a tool could be implemented. Next I'll show the symbol table generation. So after that we pass the symbol flag. You see we create this table for each name in the program. We record, such as X, we record what table it's in and what symbol it is in that table. Next we'll show the type checker on this fixtypes.c program. It returns two type errors. One is we return an integer, but we have a void annotation. The other is this display message requires two arguments. Now when we run the type checker, there are no more errors. Next we will show the IR generation, which generates an intermediate representation that is CPU independent and uses static single assignment form with ever increasing register numbers. So the next stage is MIPS generation. So we'll pass that in, and you can see we generate the MIPS assembly code. Next I want to show how the compiler is tested. To do that we use Python and the PyTest test framework. You see we have multiple tests for each stage. Take a look at the IR test. So the way this test works, and all other stages had similar tests, we pass in a source program and then an expected output that would go to standard out. And then we compile the program using a subprocess, passing in the stage we want, and then capture standard out. Sometimes we have to do some processing of the output, and then we assume the output is as we expect. Optimization. The compiler takes in a -o flag. Optionally, if you don't pass it in, it assumes no optimization. Right now there are 5 optimizations implemented. Now we'll show how the compiler optimizations work. To do that, I have a benchmarking script which I'll run, and just to quickly go over the script, basically generates the IR for each compiler optimization level, and then compiles the code for each optimization level, runs it, repeats a bunch of statistics like timing and the number of instructions that are generated, running it against this C file, which is called config for optimization. So this program assigns this value 42, and then does a bunch of iterations and computations, but it doesn't actually change the value of value. But it does a bunch of things that are easily optimizable, like adding this expression to the value, which is really just adding 0 to the value. Or things like this, which is like value times 1, value divided by 1, plus 0. This has no change to the value. Also things like calling value, sending value to a function which does nothing with the value, just returns it back. A really smart compiler would would remove all of these intermediate unnecessary work. So our benchmarking script finished, and it shows for each optimization level some statistics. So it shows, for example, that no optimization generates 266 MIPS instructions, 192 IR instructions. If you do constant folding, the number of instructions reduces by 10. Reduced to immediate, the number of instructions reduces by 8 more, and so on and so on. Each optimization reduces the number of instructions and slowly reduces the runtime as well. Note that this last optimization only removes 2 instructions, so the fact that the time went up is probably random. So just to show some of these optimizations and how it affects the IR before and after, here you're doing a constant int, followed by a constant int, and then subtracting, and then a constant int and adding. Really, since these are all constant ints, you could compute all these intermediate values at compile time, and so we turn all these instructions down to one constant int, storing it into the last temporary that was from the IR before. Reduced to immediate involves taking advantage of a MIPS special instruction add I, add immediate, which instead of having a constant into a temporary and then adding that temporary to another one, you can just do add immediate and 1 right into the temporary. And so we added a new IR form especially for this. The next optimization is Algebraic Identity, which looks for things like, here's a constant in load word, and then multiply that word by the constant. But if the int happens to be 1, the multiplication doesn't do anything. So we can replace that with the load word. Similarly with divide if it's 1, or add if it's 0, those can all turn into one instruction. Next is redundant load and stores, which is primarily taking care of this code. Here we have a value, which we store the same value into 2 temporaries, and then we take one of those temporaries and put it into the other one. We can basically remove this for free completely, and so there's only left arrows here in the diff. Finally, if we have a goto next to a label, and this label isn't referenced anywhere else in the code, we can remove both of these. And this course has left me feeling pretty empowered. So I've been a backend Python developer for the last 5 years, hoping to transition to the compiler systems programming domain. Dr. Frankel's courses in architecture, operating system, and compilers are perfect for this. In this course I learned a lot about C, how to put together a large system in C. One dream I've had for a long time is to contribute back to the CPython reference implementation for the Python interpreter. It's called CPython because it's written in C. I think this course sets me up well to be able to contribute back to the project. And so that is one of my main goals for 2021. Thank you.